Hi, good evening. This is Karthik here from ANCIT. I welcome you all to our today's webinar on system template. Let's hold on for a couple of minutes. Let's start the session exactly at 3:02.
Okay.
Okay. Hello, good evening, everyone. I welcome you all to our fifth webinar on AUTOSAR. So today we will be looking at the system template of AUTOSAR. All right. So before we go into the webinar, a quick background about ANCIT and the speaker and myself. ANCIT is primarily a tooling and engineering services company. We have been in the market from 2007. We work exclusively with automotive and aerospace industry. We build products in AUTOSAR. We build products in verification and validation. We also do custom tool developments for verification and validation and AUTOSAR tools for our customers. We offer consulting in these services, and we also do training, corporate training. All right, a quick background about me. I'm Dr. Karthik, 16 years of experience and research in automotive electronics, radio frequency electronics, and IoT. And I've been working with ANCIT for almost 10 plus years. And I'm the research director of ANCIT. All right. So today, in today's webinar, like I mentioned, we will be discussing exclusively on the system template, and we'll be focusing on AUTOSAR 4.3.1. In fact, all our webinars are focused on 4.3.1. So if you look at as a reference, you could use that as a reference, AUTOSAR 4.0 as an 3.1 as a reference. So today what we will be focusing on is we will actually try and help you develop a system description and generate a system extract in AUTOSAR. That's what we are going to do. We'll talk about what a system description is, what is a system extract, and all those things. But if you look at it in general, it talks about how the whole network is modeled, what are the ECUs, how they communicate, and all those things. This is what is meant by system description. All right, so today we will be developing a system description file. All right, so let's go to it in detail. Before we go to it, a quick recap of why we use AUTOSAR and what we have done in our previous sessions. We have started with an AUTOSAR architecture, and we found why AUTOSAR is important. The major objective of moving towards AUTOSAR is separating the application software component from the hardware. So once there is a change, once a new hardware comes into place, we could still use the application software component which has been developed and tested over the years with a few or a few changes. So that's the whole objective of why we move to AUTOSAR. That reduces the cost for the OEM as well as it improves the efficiency and the reliability of the code, because the application software completely goes through continuous evolvement over a period of time. So people don't want to waste the robust software that is built over years when there is a change in hardware. So that's the simple reason why we move from a legacy architecture to AUTOSAR architecture. One of the other things, just a quick recap, if you look at it, we have three basic layers in the AUTOSAR: an application layer, we have a runtime environment, and we have a basic software. So today we will be focusing more towards the basic software, the service template. All right, so we have talked about the application. We have built a small application software component. We have developed a runtime environment. We have done the basic software. Today we are moving into the basic software component, the first step into the basic software component. All right, from a tools perspective, this is where we are. Like say, we have done a session exclusively on AUTOSAR software application software component. We have developed a system software component description file. So this is something that we have developed. All right. So the next step, what we are doing is we are now going to move about or developing a system description file. We are going to develop a system description file, and we will also deal in detail about the system description file, and then we could do a touch upon the ECU resource description file. And once we have all these things, once we understand the basic architecture of how an AUTOSAR component structure looks like, then we could go on to specific use cases where we will look at how do we configure an RTE for our specific use case, how do we configure our OS for our specific use case. In fact, in our last webinar, we had talked about OS configuration, but we will go into details of each and every module in a session-wise manner. But as of now, our focus of the webinar for today's session is exclusively on the system description. So I just wanted to kind of talk about these four boxes. What is the software component description? What is the ECU resource description? What is the system description? And what is a system extract or an EC extract? Just wanted to touch base upon all these four boxes for a better understanding of AUTOSAR components and the structure. When we talk about a software description, when we talk about a software component description, it is primarily an application software component that we are talking about. We can create an application software component from a virtual function bus level. Then we move to an RTE level, and then we do a final implementation level. So we have touched base upon this in our previous webinars. So we have developed a application software component file using Artop. So you could refer to the previous webinar. So the next step is once you have the application software components, let's say, for example, here in our use case, we use the same example that's used in our AUTOSAR 4.3.1 architecture, which is the seat heating element example. So if you look at this particular example, we have like say one application software component, which is your heating controller, and we have an LED dial, which could be another application software component, another LED dial for the right hand side, another application software component. So we have 5 application software components. If you look at the use case is pretty simple. It's a passenger heating element. So when a passenger comes and sits, or a driver comes and sits in a seat, and he turns on the heater to say 24 degree, then this heating controller element will turn on this coil, which is the actuator, and it will set the temperature of the heater to 24 degrees. And the same will be indicated into the LED dial. It's a simple use case that we are developing. For this use case, we need 5 application software components. One for the heating controller, which actually looks at whether a passenger is seated. And once it gets a confirmation that a passenger is being seated, and it also gets an indication from the passenger or a signal from the passenger saying that turn on the temperature to 24 degrees, then it actually turns on the temperature, and the same is indicated in the LED dial. So this is a pretty straightforward use case. And like we mentioned, it has got 5 software components, application software components, and we have created these application software components on ARXML, on Artop, and generated an XML file. So that's the step 1. What we call it as creating an application software component description. Right? It's an XML file. Now what we have moved upon is we have moved to the second file, which is the system description file, where we say now we have 5 software components, software component 1, 2, 3, 4, and 5. These software components can be distributed among 3 ECUs, like we have put in our slide. We have ECU1, which will host the LED dial ka software component. There is an ECU2, which has the heating controller ka software component. And there's a ECU3, which tells you that this coil is located in another this software component is located in another ECU. So there are primarily 3 electronic control units and 5 application software components. So the whole objective of the system description is to explain how these software components are connected and where are they located, how are they distributed among the electronic control units, and how are they established a connection, an end-to-end connection. So this is the whole objective of the system description file. So if you go back, so the OEM, once he defines the functionality of the software components, the next step is he will design the communication network and distribute the software components to the different ECUs. So that is called as a system description file. So today, what we will be talking about in our webinar is we will be looking at how these 5 software components are distributed among the electronic control units, and how do we create a topological mapping on, or how do we create a mapping on how these software components which are distributed among the 3 ECUs are connected, how they establish communication. That's the objective of today's webinar. And once we have connected all these 5 software components which are distributed among the 3 ECU, then we can move on to the next step where we say for one particular ECU, let's say for example this particular ECU, ECU2, you extract all the information, right? So you extract all the information about how this particular ECU is communicating with other ECUs. That is explained as a system extract. That is actually taken and it is given to the OEM will take the system extract and give it to the tier 1 company for them to develop. Right? So this is how it works. So if you look at an equivalent of the system extract in your legacy architecture, it's a .dbc file or a fibx file or a .ldf file. There are so many files. So this is used to configure your basic software modules, right? So in the legacy system. So these are the 3 files that we want to talk about: the software component description, the system description file, that is the whole how all these software components are distributed among the ECUs and how they are connected. And once you do this, then you extract the system where you focus on a particular ECU, like say one ECU, what are the software components in it, what are the signals that are coming out and coming into the file, and how are they establishing a communication. That's called as a system extract. The next step is ECU description, where we will say that what are the hardware components that are associated or required for this software to establish. So we go more into a hardware perspective. That's the ECU description file. Right. So for the time being, our focus is for today's webinar is on the system description. All right. So this is about the SWC system and the system extract. And like I mentioned, we will be creating a complete system description file. We will show you how to create it for one software component or one ECU. You could expand the whole same for all the 3 ECUs. That will be the plan. Yeah. All right. So a system description file should always include these 5 major elements. And like I mentioned, this is AUTOSAR 4.3.1. And if you have any clarifications on this system description, please refer AUTOSAR-System Template 4.3.1 for any clarifications. All right. So a system description file will have 5 major components. We should include 5 major components. One is the system topology. The second one is the software. The third is the mapping. It should also account the mapping constraints. And finally, it should also take care of the communication and the communication stack. All right. So since the communication stack itself is a huge topic on its own, we are restricting our discussion to only these four topics, like say system topology, software, mapping, and mapping constraints. In our next webinar, we will be focusing on the communication stack, and we will help you how to author a communication stack. And once we do that, we will also integrate it with this existing system description file. So that will be the plan for the next webinar. But as of today's webinar, we will be focusing our discussion exclusively on the topology, software, mapping, and mapping constraints. So let's look at it from a theoretical perspective for a brief amount of time. Let's spend 15 to 20 minutes in understanding what these four components are and what is the importance it plays with respect to an application. And once we have that, we will use Artop as a tool to kind of build the system description module. So that will be the plan for the webinar. So going forward, let's start with the system topology. All right. So if you look at the system topology tells you that if you look at our use case, in our use case, we say that we have three electronic control units, ECU1, ECU2, and ECU3. All right, sorry, ECU1, ECU2, and ECU3. And we say that the 5 software components are distributed among the 3 electronic control units. All right, and this is the example of a system topology. So when we talk about a system topology, we have 3 important names that come to our name. One is the ECU instance. The second one is the communication controller, and the third is the communication connector. All right. So a topology is actually formed by a number of ECU instances. So what do you mean by an ECU instance? Let's say, for example, and I will come to this our own specific use case. Let's say, for example, this is the heating controller use case that we are going to implement in our Artop. So if you look at this application software component, like say as we mentioned, this will look at the status of the seat, and it will turn on the heating element and turn on the LED dial, right? So this can be broken into 2 parts. One is the LED dial left, and the other one is the LED dial right? So for a passenger who sits on the left-hand side, we use the left-hand heating controller. For the driver, we use the right-hand side component. All right. So the component still does the same function. So what we could do is we could create 2 instances of this software component in our ECU. So we create 2 instances of this software component in our ECU. This is exactly what we call it as an ECU instance. It's like an object. So we have 2 ECU instances of this software component in our ECU. And let us assume that this particular LED and coil is getting a signal, and it says that it is coming from ECU2. All right, it says it's coming from ECU2. This LED dial and this coil will respond only if it is coming from the ECU instance of the right-hand side component or right-hand heating controller. So, which means that it is an indication of the turning on the LED dial and turning on the coil of the driver. All right. So it has to make sure that this LED dial should make sure that this signal is coming from the ECU instance of the heating controller of the right hand side. If this LED dial is receiving a signal from the ECU instance of this component, this is the left hand side controller, then it is not supposed to respond. All right. So every software component is created. I mean, every ECU has n number of instances. In our use case, ECU2 has 2 instances. All right. So that's the first step. So you create ECU instances. Step number 1. The second step is every ECU instance should have a communication controller. All right. So the communication controller is the actual hardware device by which the device actually sends and receives frame. It's the transceiver unit. If I have to put a equivalent name, it's the transceiver unit that is available. It could be a CAN transceiver, it could be a LIN transceiver, or it could be a FlexRay transceiver. So every ECU instance, in order to send and receive signals to the physical bus, it has to happen through the communication controller. So each ECU instance is connected to the communication controller. One or more communication controller. It could be connected to one or more communication controller. And each ECU instance is also connected to one or more communication connector, or what you call it as the bus interface, right? We could again say, when we talk about bus interfaces, it could be a CAN bus interface, it could be a LIN interface, or whatever be the interface. Depending upon whatever protocol it is using, each ECU instance should also be connected to the communication connector. So the first step in terms of system mapping is at least focusing or limiting our discussion to our architecture. ECU2 will have 2 software instances. All right, so it can be done through multiple instantiation. It will have 2 software instances, and each software instance will have, like, say, 1 communication controller and 1 communication connector. And this will be the first step in designing the system template. All right. So once you design the communication connector and communication controller, you could group these things. You could group this physical channels. You have the physical channels. You could actually group a physical channel. It could be a CAN bus physical channel or LIN physical channel. But this grouping, it can be connected to called as a communication cluster. All right. So a communication cluster is an ensemble of ECUs. Like, say, it's a small portion of a lot of ECU instances connected. A number of ECU instances connected together, and if it is, like, say, sharing a common bus, then we call it as a communication cluster. All right. So a lot of physical channels can be connected to two or more physical channels can be grouped into one communication cluster. So this is the whole idea. Like I said, a physical channel is nothing but a bus, or it could be a CAN bus or a LIN bus or whatever it is, but it's a physical bus. Okay. So one important note that we would like to emphasize at this point of in the webinar is whenever you read AUTOSAR System Template 4.3.1 or System Template document, and whenever whenever it is referenced to ECU in the System Template, it means ECU instance. If you are reading an AUTOSAR ECU description template and you find the word ECU, then it is reference to the ECU hardware. All right. So whenever we use this word ECUs, especially in this webinar, please remember it's not the hardware that we are talking about. We are talking about the ECU instances. All right. So this is the software instance that we are talking about. So that's the first step in developing the resource template. Like we said, system topology. We create the system topology where we create the system instances, or sorry, the ECU instances. We create the communication connector and the clusters and the controller, of course, and we map all these guys together. So that's the first step in the system description. The next step is we move to the software. All right. So we move to the software composition. In the software composition, okay, so let's move to the software composition. So in the software composition part, this software composition is a little different from the application software composition that we are discussing. In the application layer, or in the application software component when we were discussing, when we use this word composition, a composition was a collection of software components. It was a collection of application software components. Here in our system, this software composition is also called as top-level software composition. We'll talk about it when we do the Artop signal. It's called as top-level software composition. The whole idea of creating a software composition in the system level is, see, whenever we design an electronic control unit and we are talking about an application software component, we know that application software components have a number of atomic software components, correct? So the tier one company or the OEM may not be interested in exposing all the application software components or all the atomic software components that they are developing, or the functional requirements of what they are developing. All they will say is some system signal is coming out of this composition, right? And as a second, another tier one company which is developing another ECU, we just have to take that system signal and work on those signals. The logic behind how that implementation is being done will not be exposed. It will be an IP of the tier one company, or it will be an IP of the OEM. So in that sense, what happens is this composition will not expose what are the atomic software components in it. It will only expose the system signal. So that is why what we do is the OEM will create something called as a software composition or a top level software composition. This software composition will accommodate all the application software components that are available in that particular thing. For example, in our use case, if you look at this ECU, the OEM will create an top level software composition which will accommodate this heating controller application software component, right? But it will only be a black box. What the OEM will say is, what is the signal that is coming? That signal is called as a signal. So the OEM will say only the system signal which is coming out of the black box. He will not mention, like, say, this is the logic that is written, these are the number of atomic units that are coming, and these are the kind of process that is happening inside how the functionality is developed. He is not going to expose all those things. He will only say he will create one black box, and that black box will contain inside that black box, he will, like, say, all these software components are there. In our case, we could say the heating controller software component is there, and you will expose the system signal. That's it. So that is the reason why we create a software composition in the system level. It is usually done by the OEM. All right. So this is the second step. Once we create a topology and a software composition, which is nothing but a black box, and you tell this is the signal that is coming out of the black box, which you call it as a system signal, then we go to something called as mapping. All right. So in the mapping, what we do is we do a different type of mapping. The first type of mapping is we map the software components. I think, yeah. This is the first type of mapping that we do, the software component mapping. The software component has to be mapped to the ECU instance. That's the first step. All right. So like we said, we have two inputs to this mapping. One is the topology, where you have already created the instances and the composite connectors and the controllers. The second input is your software composition, which tells you, okay, the system is created and this is the system signal which is coming out. Once that is done, then the next step is mapping, where you map the application software component to the ECU instance. That's the first step. Once you map the application software component to the ECU instance, the next step is the software component also has to go to an implementation mapping. Just like an application software component, when you develop an ASWC, you will have to worry about an implementation. Here again, you will have to do an implementation mapping. So several implementations can occur for the same atomic software component, and it needs to be decided and specified which instance of the atomic software component has to be attached to which implementation. All those things have to be taken care of. But primarily saying, once you do the software component mapping, the second step is to do the implementation mapping, right? And once you do these two things, then you can establish a set of constraints. Like, say, there are two sets of constraints or two types of constraints that you could look at. One is the component clustering and the other one is component separation. When we talk about component clustering, the idea is there are some software components which can be brought together in a particular ECU. And whenever I say ECU, please remember it's an ECU instance, right? So there could be, like, say, some software components which could be grouped into a particular ECU instance. So if you enforce such constraints, such constraints are called component clustering. And there are cases where some software components should not be combined in one ECU instance. Such constraints are called as component separation constraints. All right. So once we establish, one moment. Yep, there's some kind of a drawing. I don't know how it comes. Anyway. So once we do the software component mapping and we establish the constraints, the next step is to kind of do the data mapping. So primarily there are two types of application software components that can be created. One is the client server component and the other one is the sender receiver component. So if you're talking about a client sender client receiver component, then there can be, like, say, two types of mapping that are possible. If the data types used in the sender receiver are primitive data types, then you will use sender receiver to signal mapping. If the data types that are used in the sender receiver component is a composite data element, then you use a sender receiver composite element to signal mapping. So you use the sender receiver to signal mapping in case where it's a primitive data type. In this case, where you are saying composite element, where you have composite data type, then you will use a sender receiver composite element to sender mapping, right? So when you could use signal grouping and trigger to signal mapping if there are any requirements, but we limit our discussion to where we use a client to signal mapping, sender receiver to signal mapping, and if you are using a client server, you will use a client server to signal mapping. So these are the different types of signal mappings or data mappings that are available in the system template. All right. There could also be a few signal path constraints that you can exert if needed. Let's say, for example, there is a client server exhibition that is happening, or a client server communication that's happening. Then you could use a common signal path where you say both the transmitted signal and the received signal from the server follows the same path. So you could use a common signal path in such cases. There is something called as a forbidden signal path where you say some of these signals should not take this path. So that, especially in terms of safety critical systems, you could use that. And there's a permissible signal path, like say when there are one or more signals are defined in a particular path, and two signals, like say, approach the same path, then one of those signals can be chosen. So that is another option that you could pick up. Or you could also, like say, use a separate signal path for the different types of communication. So wherever there's redundant transmission, these are some examples where you could use the different signal paths. So these are some signal paths. A simple example is, like say, EC1 wants to communicate to EC2. There are, like say, different paths it could take. There's something called as a gateway. The ECU here, the ECU3 also acts as a gateway, where it takes care of switching from one CAN bus to another CAN bus, or it can also take care of routing the packets from one protocol to another protocol also. We will talk about the communication stack and the gateway in detail in our next session, but let's ignore this for the time being. Sorry. All right, so we could use something also called as a partial networking, depending on the application that we are developing. So partial networking concept is a place, or partial networking cluster is a place where you can manage the turning on and off of a particular set of ECU instances based upon, or you can activate or deactivate a particular set of ECU instances together. So that is, like say, a partial networking mechanism. A lot of ECU instances from a particular bus interface can be turned down on a particular when the particular application is not being used, saving a lot of power. So that is one used partial networking concept cluster. In the VFB level, when we use the partial network cluster, an equivalent of the partial network cluster in the VFB level is the port group cluster. So we use port groups when it comes to in the VFB level. All right, so now let's go on to develop this system model in Artop using, we shall go ahead and develop the system description file in Artop so that you know exactly how it works. And this is the summary of steps. So let's switch between these steps. The first step, like we said, is creating the topology, where we create the ECU instance, assembly connectors, and controllers, and you kind of connect all these ways. That's the first step, where in the ECU topology. The second step is, like, say, you connect this topology, like, say, the ECU instances to the hardware elements. So that's the second step, and it's an optional step. You could do it here, or you could do it in the ECU description file also, or when you create the ECU description file. So since it's optional, we are not touching that here, but we'll show you how it is being done. And the third step is you create a top composition and link all the software components, application software components, where we talk about the black box creation. So that's something that we are going to, that will be the next step. And then once you create these two files, that is the topology file and the software composition or the top composition file, we use these instances to do the mapping. So we use the first is we do the software root composition to top composition mapping. Then we do the software component mapping, and we do the implementation mapping. And then finally we do the data mapping. You could add mapping constraints and signal path constraints as and when necessary. But for our application, which we assume it's a very simple and straightforward application, and there's no resource constraint, we are not going to use this, but you could use it when and wherever is necessary. All right. So let's switch to Artop. Here we go to Artop. All right. So here's an application software component. So that I'm going to switch between these two files. So we are going to develop a system model or a system description file for this application, for this particular ECU, to be precise. And whatever we do, you could also expand it to the other ECU system. So once we do this, what we will also do in our next session is we'll talk about communication stack exclusively, and we will go on to configure a communication stack. And once we do that, we'll create a system extract, but we will not be able to do a system extract now because we don't have the communication file. That's it. So let's go on to do it. So the first step, as I said, I'm sorry, I'm just repeating this whole process again. We are going to create an system description file for the ECU, for this entire network, to be precise. And we are going to start with this ECU. We are going to start with this ECU. This ECU is also called as the heating controller ECU. All right. So I switch to Artop. All right, look at this. I've already developed an application software component, which is nothing but my ASWC. You can look at this. I have an application software component. All right. This is my application software component. These are my interfaces, and these are the ports, and this is the behavior and the implementation. So I've created a complete application software component for a heating controller, which we have already done together in our previous webinar. So you could refer our previous webinar if in case you want to do this. But now, once you have this application software component created, I bring it into this ARXML is kind of brought it. I've just brought it here into this project. All right. Now I'm going to create a system template. Okay. So I take this fellow, open a new file. All right. I will call this the system template underscore heating controller. All right. I will call this is the system template. So I'm calling it a system template file. All right. So I've created an ARXML file. The next step. Okay. So I will switch to this. Create ECU instances and connect it to assembly controllers, assembly connectors. and map it to a communication cluster. So the first step is to create the topology for this ECU. Once you create for this ECU, then you will have to replicate it the same for the other ECUs, and then you will have to connect all these three guys, which is taken care in the communication. Let's not worry about it now, right? So the first step is I'm going to create a topology for this electronic control unit. All right, so I'm going to open new child. The first step is in the topology is creating ECU instances. Okay, so I chose an ECU instance. All right, and I will name this guy as heating controller underscore ECU instance. So this is the ECU instance of this particular all right, so this is the first step. Okay, I will probably call this ECU left because I will have two instances. So I will name it as left. Primarily, if you look at this guy, I can use two. I'm going to create two instances for this guy for this particular ECU. So I will create this is for the left. All right, so this is for the left. So this call this as left. So once you create this ECU instance, next is I need to create a communication controller. So take this and I add. I'm using a CAN communication controller. So let me choose a CAN communication controller. I will call it heating. I'll just copy this guy. And I will call it controller. So this is the controller which is attached to this particular instance, right? So he is responsible for sending and receiving the frames. The next is I will have to kind of add a connector. So I add another CAN communication connector. I will call this control V connector. So I've created a heating instance, I've created a controller, and I've also created a connector. So the topology does not stop here. We also need to add a communication cluster. All right, so I'm going to create one cluster. So I'll go to AR root, right click, elements. I will choose a CAN cluster. All right, and I will name it heating controller underscore left. It's called cluster. All right. Now what we have to do is once you create the controllers, connectors, ECU instance and the cluster, we need to map all these guys, right? So that's what we're going to do. We are not map, I'm sorry, we have to connect all these guys. So I will right click this cluster, and you know that each cluster will be connected to n or more physical channels. Okay. So I'm going to add a CAN physical channel to this guy. So the cluster will be connected to a CAN physical channel. I will call this physical channel. All right. And then you need to connect it. All right. So I have connected the physical channel to the controller. All right. So the cluster is connected to the physical channel, and the physical channel is a reference to the connector, right? So that's it. Now we have to go to this connector. This connector should also be connected to the controller, right? So we are choosing this communication controller and we choose this, all right? So with this, we know that this ECU instance is linked to this communication controller and connector. This connector is a reference to this CAN cluster and the physical channel we just connected. See, it's referenced here. And this controller is also connected to this connector. So this makes the topology complete. All right. So this is the first step. I'm sorry. So in the first step, we have created EC instances. We have added communication controllers and connectors. We have created clusters and physical channels, and we have integrated all these things together, or we have, like, say, brought them together. So this is the first step. The second step is an optional step, but I just thought I will touch it upon for one moment, but we could look at it in detail when we go to the ECU description. So the second step is actually mapping the topology to the hardware elements. So it's a pretty straightforward mechanism. AR root, new child, hardware elements, H. All right. So you could actually give it a short name, Control V, and I will call it hardware element. And you could deal with it later, right? So this is how you create an hardware element. All right, where did it go? Yeah, here it is. All right, so this is your hardware element, and then you can reference it where and when necessary. But at the time being, this is how you create a hardware element, just for reference. Now, once we created this topology, the next most important step is creating the top composition. So let's go ahead and see how do we create a top composition, or I will prefer to use this word black box. So I'm going to use this. Now go back to AR root, new child, elements, use software composition. Okay, CEO composition. Yeah, here it is. Choose a composition software component type. I will probably call it heating controller left composition. Yep. All right. In fact, I will prefer to name it. One moment. Let's call it top level. Top level primarily says that it is a black box as a reference. Yeah, top level heating controller ECU reference, right? And inside this fellow, what you need to do is you need to map the whatever software components are has to be added to it. We need to create. So we need to create. Here it is. Software component prototype. All right. So software component prototype is, when you say prototype, you know, it doesn't have all those details. It's just a what do you call it? It doesn't have the definitions and things like that. It is just a black box or a skeletal structure, I would call it. Yeah. So I will call it EC instance left, soft SWC prototype. All right. Now you know that this software component, inside this heating controller, I'll just go back. So this fellow will house this is the composition, and this fellow has the one application software component, and his name is heating controller, right? So you will have to choose this. So here you have the application software component. You need to map it and bring it. So the skeletal of the ASWC heating controller type or the application software component will be present inside this top level. And what you will do is you will only bring out the signal out of this fellow. You will just say this is the signal which is going to come out of this particular application software component, period. That will be the only thing that's available. All right. So these are the two steps that are done. We have now created the topology. We have also created the software composition. This top composition is also called, I will call it as software composition. Okay. All right. Just to keep it a little simple. It's also called as a system composition, software composition. The third step is to create a system level file. All right, so this is the third step, is to create a system level file and map all the software components to the ECU instances, and also the root composition to the composition, and also take care of the implementation. So these are the three steps that needs to be taken care after you create the system level file. So we want to create the system level files. I'll go to the AR root, new child, elements, click yes, system. Here I have a system file. I will call this fellow, let's give it like say underscore system. Yep, just to keep it simple. We'll talk about all those things later. All right. The first step, once you create the system, the first thing is you need to create a root composition and connect it, right? So how do we do this? Okay, so new child, you have a root software composition. Okay, so this is the root file. Call it, you can give it a name of root, what would be, maybe underscore root software composition. All right, so you create the root software composition. Now, this is the fellow out of which the system signal will be coming, right? Once we create a controller, right? Now, this has to be mapped to the top. So I've mapped the system signal to the top level composition. So that's the first step. So here we go. You are using this. There are two inputs to the system. One is the ECU or the topology, and the second one is the top composition. So now once you create the system, the first step is to create the root composition and map it to the top composition. We have done that. We have done A now, right? Where we have created a root software composition and I've mapped it to the software composition here. Okay, top level composition. This mapping is done. So what is the next step? Now we need to map the software components to the ECU instances. Please remember, whenever I use the word ECU in this webinar, or whenever you read AUTOSAR-System Template, the word ECU refers to the ECU instance. All right. So now I create a new file and I will call it mappings. Okay. So let's go on to do the mapping. I will call SWC mapping. Okay. One moment, I will use this name underscore okay. SWC mapping. All right. New child, and I have here I have the software component to ECU mapping. That's the first step. Software component to ECU mapping, ECU instance, and you have to map it to this ECU instance. So the ECU instance is left. Okay. So this is the first thing. You will also have to connect it to the hardware element, which is here. All right. If you have not chosen a hardware element, then you can leave it. If you want to, like say, for example, partition or create some, the OEM also can say that create a partition or a specific memory where this has to be mapped. So if you want to add those things, you can bring it in the partition and all those things. But I'm just trying to keep it simple. So we do the software component to ECU mapping. That's the first step. This is done, right? So the next step is to do the implementation mapping. Okay, before we go on to do the implementation mapping, one more thing I just forgot is we have mapped it to the ECU instance. We should also map it to the application software component, right? So that also has to be taken care of. So I will add that. Yeah, and this is the target component. All right. So see here you have added the application software component also. So this makes it complete. All right. So we make the ECU instance. We created. We do a software component to ECU mapping, and we do this a reference to the application software component also. With this, the software component to ECU mapping is done. The first is, the second step is also done. The third step is software component to implementation mapping, which we are going to do now. All right. So in the software, I will take this, right click. Software component to implementation mapping. All right. So it is here. All right. In the mapping, I will call this implementation mapping, IMPL mapping. There are formalities in which you need to name also. There is some naming conventions as well. So I'm not discussing that. Okay. And we need to talk about, okay. This is the flow which we need to, controller ASWC is what we need to implement, right? So we have done that. Right, now open a new child. You need to instant mark the target component. Yep. So you have mapped the target component as well. So now what happens is you have created one black box, and inside that black box you have put your application software component, and now you have created, you're saying that there is a system, and out of this system only one signal is going to come. We are not talking about the signal. The next step is actually the signal mapping, and that we will talk about when we do the communication. So we are saying that the signal is going to come. And this is the signal the other ECU developers or other tier 1 companies will be used to will be using to kind of develop their protocols. We will not be kind of sharing the ASWC and the other what do you call functional aspects of our design, which will be an IP of the company. All right, so we'll ignore mapping constraints, and so for the time being, you could add mapping constraints. You could club a couple of software components in one ECU instance, or you can say that these software components should not be clubbed together in an ECU instance. You could add that as and when necessary. Let's go to data mapping. Just touch base upon it. We will not have data mapping because we haven't created the signal path and all this stuff. So we will create mapping. Okay, here is it. Okay, one moment. Let me just bring it to the right to see. Yeah, here it is, mapping. Okay, new child. Okay, here we have yeah, the data mapping. There are two types of. Let me just switch to this for one moment. There are two types of communication that's happening. One is the sender receiver and the client server, and we'll use primitive data types to communicate between these two software components. So since we are using primitive data component, I will check new child, I will take mapping, and I will use sender receiver to signal mapping. If you are using a composite, then I will probably choose this guy, but I'm using a primitive data type. So I'm sender receiver to signal mapping. This is something I'm choosing. And the direction is this fellow is sending the signal out. Okay. Once I create the system signal, I can map it to the system signal. But at this point of a time, since we are not touching the communication side of things, this is left blank. Maybe in the next webinar, we will do this when we create the communication stack. All right. And the next step is to kind of new child data mappings. We have a client server also. So I'm doing a client server to signal mapping. And once I do that, I will also kind of, this direction is, since it's a client, it's in, so telling it's a client. So here again, we don't see what is the return signal and all those things, primarily because it's we have not what do you call, created the communication path. Once we create the communication stack, then we could actually do this whole process and complete this. So this is something that we have done for one, if we have to go back to this guy. So this is something that we have created for this particular ECU instance. You can replicate it. When you say multiple instantiation, when you design the application software component and you say multiple instantiation is supported, then it can be instantiated. Okay. And then what you do is you could also create n signal paths, n ECU instances, for ECU instance 1, ECU instance 2, and 1, 2, and 3. and then we will create a communication path between all these ECU instances, and that makes this whole system template. All right. So for the lack of time, we just restrict our scope to this. We could go on to create this LED car ECU instance and the heating coil car ECU instance and map all these things through a communication channel. So that's something that communication stack is something that we are not touching upon this thing. It's an exclusive topic which we thought we'll reserve it for the next session. And like our next session, like always, it's like on the first working Thursday. I'm sorry, it's on the first Thursday of every month. So our next session will be on AUTOSAR communication stack, and we wanted to do one exclusive session on AUTOSAR diagnostics stack as well. So that our next session will be on Jan 7, 2021. So that's pretty much from our side. And like to summarize what we have done. This is the summary of steps that we have done. We have created a system template, which means it's a DBC file equivalent in legacy, where you have number of users and you also tell how these issues are connected and the signal flow between these guys. So that's the system template. And we have it has 5 components. A system template usually has 5 components. The software topology, software mapping and mapping constraints. We have talked about all these 4 and how do we do it in Artop. We have a communication stack which is left. We will definitely do that in the next webinar, which we have reserved for the next webinar. And a quick feedback from all our fellow participants in the webinar. There's been a lot of people who've been asking to kind of go to configuration directly, like say people want to do RTE configuration, like OS configuration, all those things directly. But we personally feel if you don't understand how this whole template works, these are all like say 700 or 1600, 700 page documents. No one has got the time to read all these documents. So we're trying to simplify this whole thing and give it in our NAR. You could, as and when you like say have time, you could go through these documents. All these documents are based on AUTOSAR 4.3.1. And we'll definitely come to RTE configuration, OS configuration, and we'll do specific use cases and all those things. As a token step, this whole month of December, we are going to build an application software component in the AUTOSAR standard. So you can follow our AUTOSAR LinkedIn community. Bishmak, if you can put the link in the group. So this whole month, every week we will be publishing. Yeah, so if you can just put the link in our the learning community link in the group. So starting from tomorrow, we will be working on writing 5 to 10 minutes blog where you will go on to build the application software component from here to here. You will do this whole process, and you will be able to build an application software component in an AUTOSAR format. That's something that you will be doing on a parallel note. And once we do this, we will also start on RTE configurations for specific use cases and all those things. And if you have any specific requests, we can take that as well. So that's it from us for the time being. We hope to engage you in our next webinar. And please do follow us in our AUTOSAR learning community and work with us. And if you have any interesting use cases you want us to work on, or if you want to add something or contribute something, we'll be more than happy to accommodate you in our learning community, and we look forward to building a very strong learning community. Please to join our AUTOSAR learning community. Ishma, if you can put the link on the group. Yeah, so people can just click on it and join. And if you have any questions, I will be more than happy to take those questions as well. Yeah.
I think there are a few questions in the Zoom chat. Karthik? Karthik, are you there, Karthik?
So there are a few questions. I'm sorry, I got the internet just got disconnected. It's pretty unstable here for a moment. What are the questions? Participants. Bhishma, can you help me locate where are the questions put up?
Yes, Karthik. Just click on the chat. Near
Oh,
the
here, chat, is it? Okay. But this is the only question, is it?
Yeah, yes. It starts with, could you again explain ECU instance briefly?
Where is it? I don't find the questions. Oh, I think since we got disconnected, I lost the questions, is it?
Okay, no problem, Katya. I will post you privately.
Where? Like say, okay. Bhishma, can you just copy those questions and put it somewhere, maybe on our Skype group or something?
Yeah, Katya.
Okay, just hold on for one moment. Sorry, I lost the questions. All right. Okay, here it is. The first question is, hello everyone, FFE. Okay, could you please explain ECU instance briefly? Okay. See, ECU instance, if you look at, like say, it's a software component, all right? It's a software component, okay? And an ECU instance can actually contain. Okay, maybe I can give you a different example. Let's say, for example, we are like say three people communicating. There is the question is asked by some FFEF. I don't know. I'm sorry, I don't have your name. So let us say, for example, there are three people who are communicating. All right, and say, for example, me, myself, Bhishma, and Malay are three friends, and we are chatting on the Skype group. Okay. If a particular data is sent from me to exclusively for Malay, then that data has to go from me exclusively to Malay. It should not go and trigger, or it should not go and work with Bhishma, correct? So that Malay, Bhishma, and Karthik are the three ECU instances to whom the data is forwarded. Okay, if I have to put it in a simple use case, that is something. So it will have to go to that particular ECU instance or that particular user. So if you look at our example, I'll just share my screen. Okay. If you have to look at from our example point of view, I will create one ECU instance, a software ECU instance. That software instance is for LED dial. This is could be one software instance, and this is on the right hand side. So if this LED dial receives a signal from this software instance, hardware heater controller, right, then it will trigger. If it receives an instance or a signal from this particular instance, then it will not trigger it. All right, because it's not intended to this particular ECU instance. All right, so ECU instance is more of a software instance, just like say a user or like what we talked about Annamalai and Karthik. That's a pretty straightforward metaphor that you can think of. Okay, and the next question is, this session is for developers, testers. This session is for developers, testers, and even if you're a mid-level architect in AUTOSAR, it is good. Our objective is to, kind of debrief AUTOSAR and demystify AUTOSAR and make it simple for everyone to understand. It's irrespective of whichever environment you come from, I'm sure this is going to help you. It will help you understand. Especially when you're talking to customers, or especially when you're reading some files, you'll be really able to understand what it is. If I have to use my friend's Malay's name, it is to Google enable you. That's the right word he always uses. Yeah. And from me to everyone, we will address all your queries at the end of the session. Okay, this is something. Okay, there's a couple of weekend courses that we do as well, just kind of you're interested. Okay, here are a few questions as well from Girish Chandra to everyone. Why do we need two ECU instances here? Then you will configure the ECU for only one instance, right? Yes, you are right. You don't need two instances, but in the application software component, what I will do is when I build the ASWC, I will support multiple instantiations. So I can copy one instance in one memory location and another instance in another memory locations. Both those software instances will be doing the same work, but it will be supporting left side and right side. One for passenger and the other one is for what do you call driver. Okay. Can we get Artop software? Artop is a test authoring tool. Only a few companies who are members of AUTOSAR have access to Artop. We are building our own small play test authoring tool. We are going to make it public for people like who are not in professional and who are like say who want to learn AUTOSAR. They could use this test authoring tools. It will be released before January 15th. So that's a timeline. So once it's there, we'll share it in our group. And you can join our AUTOSAR LinkedIn learning community. I think, yeah, here it is. You have a link. You can just click on that link and you'll have all those webinars, the previous webinars available there. So you can just do from Sridhar. Yeah, so that's something. And like I mentioned, we will also be kind of running this month. We will be helping you, right? We are going to do small video tutorials and blogs to help you build an application software component. If you have more queries, please post them on our LinkedIn group. We'll try and make it very interactive and help you build an application software component as per AUTOSAR standard. Basic we can do, we can start small, but there should be some kind of an improvement. That's a whole objective of the learning community. You can register and download the demonstrator. Yeah, so there is somebody who's given a tip. And this is the learning community. Yeah, Sridhar will definitely accept your request. And how to view this is again something you can view all our videos in the LinkedIn community. Yeah, that's pretty much from our side. Thank you, gentlemen. Thank you so much for being such a lovely audience. Thank you for your patience. Appreciate it. We look forward to host more sessions in the coming week. Coming months. Okay, so there is like say a particular question. So normally, which software component is used by the developer? There are quite a few software components. Like say, Vector comes up with its own AUTOSAR stack. Electrobit has its own AUTOSAR stack. MATLAB comes with its own software component. But as a functional software developer, you don't need any stack. You need to understand C thoroughly to kind of go and implement a functional level implementation, which is not defined in AUTOSAR standard. AUTOSAR only defines the structure. Functional description is not a part of the AUTOSAR standard. So what do you mean by functional is how should it communicate? How should it send signals? All those things are structural elements. How it should receive. These are like say structural elements, but once it receives the signals, what it has to do with that signal, how it's going to work, that functional requirement is not part of the AUTOSAR standard. It's more of an algorithm which is driven by C, embedded C to be specific. Yeah, thank you so much, guys. Thank you so much for your patient listening. We look forward to host more interesting webinars in the future sessions. Yeah, have a nice weekend. You all have a happy Christmas and happy New Year.
Thanks, Karthik.
Thank you, Bhishma. Thank you, Manzoor, and thank you, Malay. Thank you so much.
Bye. Take care.
Thanks, Prashant.